Welcome back to Talk Tensors. Today we're jumping into a really interesting paper.
Yeah, this one caught my eye. It's titled Identifying Cooperative Personalities in Multi-Agent Contexts Through Personality Steering with Representation Engineering.
Quite a mouthful, but the core idea is fascinating. It's basically looking at how we can influence the personality of large language models, LLMs, to see how it affects their ability to cooperate.
Exactly. And this is becoming super important, right? As LLMs get more autonomous, figuring out how they interact, especially in groups or teams, is critical.
We've seen some amazing potential, but also some, let's say, unpredictable behavior when they work together or against each other.
Right. So this paper uses the iterated prisoner's dilemma, a real classic in game theory, as a test bed.
Okay, so they're trying to see if making an LLM more, say, agreeable makes it a better team player in this specific game context.
Precisely. And they use this technique called representation engineering to actually tweak these personality traits.
Representation engineering.
Yeah.
Let's unpack that a bit. How does that work?
Well, think of the LLM's internal state, its thoughts, if you will, as these complex patterns of numbers or representations. Representation engineering is about finding the patterns that correspond to certain traits, like the big five personality traits: agreeableness, conscientiousness, openness, extroversion, neuroticism, and then subtly boosting or reducing those patterns.
So you're not just telling it to act agreeable in the prompt, you're actually nudging its internal processing.
Exactly. You're steering its internal state to be more agreeable or conscientious or whatever trait you're targeting. The hope is this leads to more consistent behavioral changes.
And they wanted to see if this steering actually changed how the LLMs behaved in cooperative games.
Yeah. The big question was, do these steered personalities make LLMs cooperate more effectively, or perhaps make them more vulnerable? Or maybe both?
Okay, before we dive into their results, maybe give us a little background. Why this focus on personality and cooperation in LLMs now?
Well, it builds on earlier work. People noticed LLMs could show sophisticated reasoning, even social inference sometimes. But other studies, like some simulated war games, showed they could also be unpredictable, sometimes adversarial, easily exploited even.
So there was this gap, potential for cooperation, but also risk.
Right. And researchers started thinking maybe drawing parallels with human psychology could help. In humans, personality is a big factor in decision-making, cooperation, trust.
So the idea was, could the same be true for LLMs?
Kind of. People had experimented with giving LLMs different personas through prompts or looked at how traits might affect vulnerability to bad prompts. This paper takes it a step further by using representation engineering for more direct control over these traits and testing it systematically in the prisoner's dilemma.
It feels like a natural progression, applying psychological frameworks to AI behavior. Okay, so let's get into the nitty-gritty, the experimental setup. You mentioned the iterated prisoner's dilemma.
Yeah, the IPD.
Yeah.
Classic scenario. Two players repeatedly choose cooperate or defect. Mutual cooperation is good, mutual defection is bad. But defecting while the other cooperates gives the defector the best individual outcome and the cooperator the worst. The iterated part is key. They play many rounds so they can learn and react to past behavior.
Builds up a history, allows for strategy.
Exactly. And they design three main setups to test different things.
All right, lay them out for us. Setup one.
Okay, setup one. You have player A, which is the LLM whose personality is being steered. Player B is a simple rule-based agent. It follows fixed strategies like always defect, always cooperate, or just random.
So testing the steered LLM against predictable behavior, what did they measure?
They looked at four things. First, troublemaking rate, basically. Does the LLM stab the opponent in the back after the opponent cooperated? Measured against the always cooperate opponent mostly.
Makes sense. What else?
Exploitability rate. Does the LLM keep cooperating even when the opponent is just defecting over and over, measured against always defect?
The doormat factor.
Kinda, yeah. Then, forgiveness rate. If the opponent defects, then cooperates, does the LLM go back to cooperating? And finally, retaliatory rate. If the opponent defects, does the LLM defect back?
Okay, comprehensive look at reactions. What about setup two?
Setup two added communication. Before each round, player A, the steered LLM, had to announce whether it intended to cooperate or defect.
Oh, interesting. Adding a layer of potential deception.
Exactly. Player B here wasn't just fixed rules. It was either altruistic, trying to help player A based on its stated intention, or selfish, trying to exploit player A's stated intention for its own gain.
And the key metric there must have been
the lying rate. How often did the LLM say one thing and do another?
Got it. And the third setup. Sounds like the main event.
It was. Setup three. Both player A and player B were LLM agents, and both had their personalities steered.
Ah. LLM versus LLM, both with potentially different engineered personalities.
Exactly. Here they measured the total score. Think of it as the total combined prison time, you want this to be low, and the personal score, which was the difference in prison time between the two. So how well did they do collectively, and did one systematically outperform the other?
Okay, that covers the core experiments. You mentioned they did some preliminary tests first.
Yeah, just quick baseline checks with some available open source models, Llama 3.1, Gemma 2, Mistral Nemo. They ran them through the prisoner's dilemma without any steering.
What did they find?
Basically, that cooperation wasn't great out of the box. The rates varied, but none were consistently optimal cooperators. Some tended to defect quite a bit. It showed there was room for improvement, setting the stage for the steering experiment.
Right. It validates the need for something like steering if you want reliable cooperation. Now, remind us again about the steering method itself. How did they find that vector for agreeableness, for instance?
They used contrastive prompts. So they'd feed the model prompts designed to elicit, say, highly agreeable responses, and prompts designed to elicit highly disagreeable responses. Then they looked at the difference in the LLM's internal activation patterns, these high-dimensional vectors between those two conditions.
And that difference gives you the direction for agreeableness in the model's internal space.
That's the idea. They identify this steering vector. Then, during the actual game, they add a scaled version of this vector back into the model's processing. At specific layers, they used layers Nidec-5 to Nidec-20, sort of the middle to late layers.
Why those layers?
The thinking is that manipulating the very earliest layers might be too low level, and the very last layer might be too superficial, too close to just changing the output text. The middle layers are thought to influence more abstract reasoning and behavior generation. They used a scaling factor of 3.5 to control how strong the personality push was.
Okay, clever stuff. So the moment of truth, what were the results? What happened when they ran these steered LLMs through the setups?
All right, setup 1, the LLM against the fixed bots. Big finding. Steering towards agreeableness, conscientiousness, and openness completely dropped the troublemaking rate to 0. These LLMs wouldn't defect against a cooperative opponent.
That sounds promising for cooperation.
It is, but here's the trade-off. High agreeableness, specifically, caused the biggest jump in the exploitability rate. It went up by 0.44 compared to the baseline.
So the most agreeable LLM was also the most likely to be taken advantage of by the always defect bot.
Exactly. It kept cooperating even when it clearly wasn't working. Agreeableness also massively increased forgiveness up by 0.75 and decreased retaliation down by 0.75. So very forgiving, not very vengeful, but potentially naive.
That really highlights a potential dilemma in designing cooperative AI. Okay, setup 2 with communication and lying.
The unsteered baseline model actually lied quite a bit, a median lying rate of 0.70, but steering towards higher agreeableness and higher conscientiousness significantly reduced this lying.
Interesting. So those traits promoted honesty.
It seems so. And this reduction in lying happened regardless of whether the opponent was playing the altruistic or selfish strategy. The opponent's behavior didn't seem to make much difference to the LLM's honesty when steered this way.
That's quite encouraging, suggesting these traits might foster intrinsic honesty. What about setup 3, the LLM versus LLM interactions?
This is where it gets really interesting for multi-agent systems. When both LLMs were steered towards high agreeableness, their combined prison time, the total score dropped by 60% compared to the baseline. Huge improvement in collective outcome.
Wow, so agreeable agents working together really achieved much better results for the group.
Yes, agreeableness and also conscientiousness consistently led to the best collective scores. And it's that they often led to the worst individual outcomes for those agents.
Meaning they prioritized the group's success over their own individual score.
That's how it looks. They seem to avoid actions that would hurt the pair, even if it meant getting a slightly worse personal result compared to their partner. And the honesty aspect seemed key, even if one agent was slightly exploited. The overall honesty associated with agreeableness and conscientiousness helped the group outcome compared to scenarios with less trustworthy agents.
So, agreeableness and conscientiousness seem to promote a kind of pro-social, group-oriented behavior, even at personal cost, and foster honesty, which benefits the collective. Did they connect this back to human studies?
They did. They noted that these findings resonate with research in human psychology and behavioral economics, where higher agreeableness in humans is often linked to increased cooperation rates in similar prisoner's dilemma games.
Fascinating how these parallels emerge. So let's try and synthesize this. What are the big takeaways?
Well, the main one is pretty clear. You can influence LLM cooperation in these strategic games by steering personality traits using representation engineering. It demonstrably changes their behavior.
But it's not straightforward. There's that crucial trade-off.
Absolutely. Traits like agreeableness boost cooperation and honesty, which is great. But they simultaneously increase vulnerability to exploitation. You can't just dial up niceness and expect everything to be perfect.
Which has major implications for designing real-world multi-agent AI systems, right?
For sure. If you're building AI teams for, say, negotiation or coordinating autonomous vehicles, you want cooperation.
Yeah.
But you also need resilience. These findings suggest it's a balancing act. You might need to instill prosocial traits, but also build in safeguards against exploitation.
And the finding about honesty linked to agreeableness and conscientiousness is also pretty significant.
Yeah, the idea that we might be able to engineer more inherently trustworthy AI agents is definitely appealing, though it also raises ethical questions, of course.
We should touch on those. What are the broader implications here?
Well, potential applications are huge. More reliable AI collaborators in science, business, logistics. But ethically, engineering personality is tricky territory. How transparent should it be? What are the risks of unintended consequences? Could it be used manipulatively?
Serious questions we need to grapple with as the tech develops. And of course, this was mainly in the context of the prisoner's dilemma.
Right, a limitation they acknowledge. It's a simplified model. We need more research to see how well these findings generalize to more complex real-world scenarios with different rules, incentives, and interaction types. Does it hold across different LLM architectures too? Lots more work to do.
It definitely lays important groundwork, though. Okay, let's shift gears slightly to our novel notions segment. Based on this paper, what's a potential future research idea that springs to mind?
One thing I was thinking about is what you might call meta-personality steering.
Meta-personality steering. Go on.
So instead of the personality being fixed, could NLM learn to dynamically adjust its apparent personality based on who it's interacting with?
Like, it starts out agreeable, but if the other agent keeps defecting.
Exactly. It might learn to dial down the agreeableness and maybe ramp up its retaliatory rate temporarily, becoming firmer. Then, if it encounters a cooperative agent, it shifts back to being more agreeable and forgiving.
So, adaptive social strategy baked into the personality steering. How would you even approach that?
You might use reinforcement learning. The reward signal wouldn't just be about winning the game or maximizing points, but could also incorporate measures of sustainable cooperation, resilience, maybe even the perceived fairness of the interaction over time. It builds directly on this paper's findings about the effects of different static personalities.
That's a cool idea, AI that learns social flexibility. What's another notion?
Another direction, maybe more ambitious, is looking at the emergence of social norms in large populations of LLM agents.
Okay, scaling up significantly from the two-player games in this paper.
Right. Imagine simulating not just two, but hundreds or thousands of these LLM agents, maybe with a mix of different baseline steered personalities, interacting over long periods in a more complex environment than just the IPD.
What would you be looking for?
You'd look for whether stable patterns of behavior emerge across the population. Do certain strategies become dominant? Do implicit rules or norms about cooperation, punishment, or fairness develop spontaneously? You could analyze the statistics of interactions, look for feedback loops.
Like watching artificial societies evolve their own cooperative conventions.
Sort of, yeah. It draws inspiration from evolutionary game theory and studies of cooperation in biology and sociology, but applied to these complex AI agents. Could we see the conditions under which cooperation becomes the norm in an AI population? This paper gives us the tools to manipulate individual agent traits. The next step could be seeing what happens at the group level.
Both fascinating ideas. And just to be clear for everyone listening, these are speculative thoughts, right? Just directions future research could take.
Absolutely. Food for thought based on the groundwork laid by this paper.
Well, this has been a really insightful discussion. The key takeaways seem to be the clear link between engineered LLM personality and cooperative behavior, that critical trade-off between cooperation and exploitability, and the potential with careful design, to foster more honest and group-oriented AI agents.
Definitely. Understanding these dynamics is only going to become more crucial as AI agents play bigger roles in collaborative systems.
And if you want to dive deeper into the methodology, the specific results, the prompt, designs, all the technical details, the link to the full paper, identifying cooperative personalities in multi-agent contexts through personality steering with representation engineering is in the show notes.
It's a solid piece of work, worth the read if you're interested in this space.
So that brings us to the end of this deep dive. It leaves us with a lot to think about, especially that central question. As we get better at shaping AI personalities, how do we ensure we're optimizing not just for cooperation, but for robust, fair, and ultimately beneficial interactions in the complex systems they'll inhabit?
A question we'll likely be revisiting often here on Talk Tensors.
Indeed. Thanks for joining us.